Hi, everybody. Today we're going to look at MCAT Organic Chemistry Review. So we have a really good diagnostic test that specifically looks at 50 different questions with the passage on organic chemistry review. I think if you can do that, you'll be in pretty good shape. So everything we have here is designed from the AAMC content outline. As you can see, we have carbon and functional groups, induction and resonance, isomers, stereochemistry, alkanes, alkenes, alcohols, including SN1, SN2. We're going to look at Carbonyl Chemistry as well as Carboxylic Acid Derivatives. So here's carbon. Everyone's familiar that carbon is number 6, so it has 4 electrons in its outer shell, so its valence is 4. So then you see a saturated alkane on the left up here, and over here we see an alkene with its sp2 hybridized with 120-degree bond angles. There's pi electrons here, and there's the alkyne that's linear. It's sp, and there's no alkynes in human biology, which is kind of interesting. So there's key functional groups we're going to go over. Here's just some of them. There's other ones as well. So we have alkyl halides, we have alcohols, aldehydes, and ketones. Here's the anhydrides. We're going to look at reactions for all of these, how to make them, and what they do in chemical reactions. Here's acid halides. Carboxylic acids, of course, are quite important. Amines, amides, and acetals and hemiacetals. We'll look over those, but we're going to look at them in the context of sugar chemistry. So one important thing that you might recognize that many of these groups can either be hydrogen bond donors or acceptors. Take an alcohol, for example. It's a hydrogen bond donor. Over here, you see the arrangement with hydrogen bonding. You see an electronegative atom like fluorine, oxygen, or nitrogen. Covalently linked to hydrogen means you're the donor. And over here is an acceptor that could be a nitrogen, oxygen, or fluorine itself. So if you look at the alcohols, we said it's a donor, but the aldehyde is an acceptor. So induction is important to know because that determines a lot of chemistry as well as other physical properties of molecules. So induction is basically the unequal sharing of electrons. And so one easy thing to see is water. Here we see the polar bonds and polar covalent bonds in water here. We see oxygen, by virtue of its high electronegativity, is pulling electrons towards itself. And as a consequence, it generates a partial charge of negative on itself, but these hydrogens that it's bound to generate a partial positive charge. And what we have is a dipole moment. Over on the right, we see the carbonyl, and we're going to see this again. This is showing you that the oxygen is pulling electrons from this carbon towards itself, generating a partial negative charge. And as we see, oxygen loves to be negatively charged. So there's no better way to make oxygen angry than to put a positive charge on it. As a consequence of this induction event, what happens is that the carbonyl carbon here generates a partial positive charge, and that's considered an electrophilic center, which can attract a nucleophile. So this formulates the basis for why carbonyl compounds are often very reactive. Now we see induction with sigma bonds. Over here in panel B, we see a carbocation. And we know that carbocations have differential stability, whether or not they're a tertiary, a secondary, or a primary. Tertiary is the most stable of the three. And because what happens is these alkyl groups, these R groups are inductive, and they donate electrons towards the positive charge. And since carbon's electroneutral, it doesn't want to be too positive, it doesn't want to be too negative. It's reactive when it's a carbocation, it's reactive when it's a carbanion. What happens then is that you can stabilize this positive charge on the actual tertiary carbocation. And you can do it with 3 better than you can do it with 2. That's why tertiary is more stable than secondary. But so just as we see that carbocations have alkyl groups that donate electrons towards the carbocation, we can see induction going the opposite way too. So what you see here is a series of chlorinated compounds. They're basically derivatives of acetic acid. We have trichloro, dichloro, monochloro, and good old plain old acetic acid itself. And so these electronegative chlorines can actually pull away the electrons. And as doing so, they make this proton more acidic, as you can see by the low pKa value. And you recall that the lower the pKa value, the more acidic the proton is. And so what you see then, as you decrease the number of electronegative chlorine atoms bound to the carbon, the pKa values rise from 0.7 to 4.86. So this induction event's occurring through sigma bonds. It's pulling electrons towards itself, and one of the consequences is that that proton becomes more acidic. Now, just as induction is to sigma bonds, resonance is to pi bonds, and the classical structure is, of course, benzene itself. And here's the structure of benzene that we all know of, okay? Has C6H6, but we know we can draw two different Lewis dot versions of benzene by alternating the position of the double bonds within the ring. And the true structure you see here has this circle in the middle, which denotes the fact that these electrons are delocalized and they're basically being shared amongst all 6 atoms in the benzene ring. And you can actually show that the bond lengths are intermediate in benzene between single and double bonds, showing you that the average bond length is somewhere between a single and a double bond. So you can also see the resonance structures of aniline. What you can see is that these electrons, these lone pair of electrons from nitrogen here, can actually share amongst the carbons in the ring. And by doing this, what you can generate are resonance structures. And notice that the second resonance structure has a positively charged nitrogen, and you have a negative charge on this carbon over here. Whenever you draw resonance structures, you have to appreciate that the sum of the charges must equal the parental molecule. Now, when you add on to aniline by electrophilic addition to the benzene ring, what you're going to do is you're going to add on groups that favor the position of the carbanion here. And so you see the carbanion can be here, these electrons can jump in here, move these over this carbon, so you have another resonance structure. And what you can see is that the carbanion is immediately adjacent to the position that's attached to the nitrogen as ortho. It's also distal, which is going to be para, but you don't see a lot of meta. So what you can see then is aniline is going to add on to itself at these particular positions based upon the resonance structure intermediates. So we've seen carbocation stability with tertiary, secondary, and primary. Now I added on benzyl, allylic, methyl, and vinylic or vinyl. And so what you can see is tertiary is more stable than a benzyl. Over here on the benzyl, you see the carbocation at the end of this carbon that's outside the ring. But what can happen through resonance is that this carbon, positively charged carbon, can be shared amongst the constituents in the ring. And by having no one carbon experience the total positive charge, what happens is that you generate stability of the carbocation. Carbon doesn't want to be positively charged. And so we can explain the hierarchy of carbocation stability in these molecules through both induction and resonance arguments. So now we'll turn to isomers, and we know that the same formula, but different spatial arrangement of atoms. The first one to see is conformational. Conformational is rotation around sigma bonds. You're not actually breaking bonds, you're just rotating around sigma bonds. So if you take this molecule up here and you rotate around carbon number 1, what you can do is get a conformational isomer. You should appreciate the nomenclature. The hatched lines represent a chlorine in the back of the plane, but the wedge represents the hydrogen that's sticking out into your space. So it's a way to represent atoms in 3 dimensions on a 2-dimensional surface like a piece of paper or a slide screen. So if you look at this from a Newman projection, what you can see is that this is the carbon right here. What you can see then is that by rotating around C1 and C2, what you can find is that the position of the methyl group and the chlorine group varies as a function of the degree of rotation, such that the most stable one, the lowest energy, is called anti, and it's when you have the methyl as far apart from the chloride as possible, and this limits electron-electron repulsion. So you see here in the eclipsed, when they're actually the closest together, that has the highest energy and it's the most stable of the conformational isomers of this particular compound. So conformational isomers also exist in cyclohexane as well as other 5- and 6-membered ring derivatives. It's difficult to put a 6-membered ring into a plane. And so what happens is that it puckers up. And there's the chair conformation, which is more stable than the actual boat conformation. And we see this applied to a lot of our sugar chemistry with glucose and its derivatives. So over here is a representation of the actual boat structure, or excuse me, the chair structure. What you see here are axial and equatorial groups. And we know that the groups want to be as far apart as possible in order to prevent electron-electron repulsion. And so what you can do then is draw this out and convert axial and equatorial such that you can see this molecule down here is cis-1,2 dichlorocyclohexane. And so you have an axial and an equatorial here, so it's cis, not trans. So you should be able to convert from this chair structure written this way, as well as the depiction in this format with the wedges and the hatched lines. Structural or constitutional isomers have the same formulas, and we see this with the derivatives of pentane. We have N-pentane, isopentane, and neopentane are all C5H12, but they have different physical properties. What we see is that the melting and boiling points are different. For example, with N-pentane, what you can do with this linear molecule is you can get more intermolecular packaging together, like they can spoon together easier. As a consequence of that, N-pentane is a liquid at room temp. Okay, but neopentane with this branch can't do this nice intermolecular packing. And so what you get then is that it's a gas. Basically, its boiling is 9.5 C. Geometric isomers have rotation hindered in some part of the molecule. Now, this could happen in ring structures on the right, or it could happen with molecules with double bonds because you can't rotate around a double bond. So what you see here is trans-2-butene versus cis-2-butene. Yes, they'll have different physical properties like boiling point. So what you see here then is that if you're on the opposite side of the double bond on each carbon, you're trans, but if you're on the same side, you're actually cis. Now, you can also get geometric isomers in these structures here, these ring structures here, because there's no rotation with the ring. Here's the cis and the trans as well. So now we turn probably to the most important aspect of stereochemistry and isomers. And this is chirality of carbons. Other atoms can exist chirality, but the MCAT will probably exclusively test you on carbon chirality. So stereoisomers differ in their three-dimensional spatial arrangement. Okay, and so what's a chiral molecule? Well, chiral in Greek means handedness. So these molecules have like a left hand and a right hand, and carbon stereocenters they have to be sp3 hybridized. So it's a carbon bound to 4 unique substituents, and in general, there's a rule that if you have an n number of chiral centers, you'll have 2 to the n stereoisomers, but we'll see an exception to that in a moment. So the simplest way to think of stereoisomers and carbon chirality is to look at your left and right hands. So your left and right hands are basically mirror images of each other. They're not superimposable upon each other. And what we can do is we can designate one as R and one as S, and we'll discuss that in a moment. So this was discovered in the old days by Louis Pasteur. That's right, he wasn't just a biologist, he was actually trained as a chemist. And so what you have then is non-superimposable mirror images are said to be enantiomers, okay? Now, these enantiomers are gonna have identical physical properties with one important exception that was discovered in the 1800s, and that's how they rotate the plane of polarized light. So let's take a look. So here you have a light source, okay? And it's going off in all 360 degrees, but if you polarize it, what happens, you just bring one ray of light comes in. And here's your sample cell with your compound that's basically chiral. It could be the R or the S, and we'll do the R versus S later. R is like the right hand and S like the left hand. And if you shine light on that sample that's chiral, what will happen to it, when the light comes out, it actually rotates the plane of polarized light by a degree called alpha. And so what you see is that the left hand will rotate at alpha and the right hand will rotate at negative alpha. It's pretty interesting how that works. So you can also have circular polarized light. And circular polarized light gives rise to the concept of circular dichroism. So let's take a look at that. So here's linear polarized light. But you can have left-handed and right-handed circular polarized light, and there's machines that can make this happen. So this concept of circular dichroism arises when asymmetric molecules like chiral molecules, or proteins are chiral too, preferentially absorb light of a given handedness. So what you can do is generate a CD spectra. So you can take your protein sample, for example, shine circularly polarized light from left-handed and right-handed at various wavelengths. And you generate what's called a circular dichroism, or a CD spectra. And that spectra is the difference in absorption between the left-handed and the right-handed circularly polarized light. And so you get positive values when the left-handed light absorbs more than the right-handed, and you get negative values when the right absorbs greater than the left. And if they're equal, then you're going to get no circular dichroism at all. That's what an achiral molecule would do. That's what a molecule of no net asymmetry would actually do. So this technique is on the AAMC practice tests. So it's definitely on the MCAT. This is a concept of polarity merged with the lab technique of absorbance spectroscopy. And so what you can do then is imagine that if you have a protein that has a conformation that's changing, the formation of an alpha helix, the dissociation of an alpha helix, the movement of an amino acid as it becomes modified by some sort of chemical modification like phosphorylation, etc. What can happen is that as the molecule moves, it'll have a bias in its ability to absorb either left or right-handed circularly polarized light. As a consequence, what will happen is it'll come up on the spectra. So CD spectra is often used to look at the secondary structure and the conformation of proteins. So the pharmacological importance of stereoisomers is really paramount. The best example I know of is naproxen. This is an over-the-counter pain med. So it's a non-steroid anti-inflammatory drug. And so what you can have is the S and the R, and we're going to determine in a moment how to differentiate between the two. So enantiomers have opposite configuration at each chiral center, okay? Now, if you're 50-50, that is, if you're a racemic mixture where the amount of S equals the amount of R, then there'll be no net optical activity. There'll be no net rotation of the plane of polarized light. But so the S version is the pharmacologically relevant version. It binds to and inhibits the cyclooxidase enzymes, and this, of course, gives rise to how it has its therapeutic effect. But the R version is toxic. So in chemistry, when you synthesize these things, you often get both products formed. So the question is, how do you separate the stereoisomers? This is actually on the AAMC MCAT content outline. We have a passage on our stereochemistry diagnostic that actually goes over this. And so there's a couple techniques to actually separate stereoisomers. And remember, since the S and the R have identical physical properties, with the exception of how they rotate the plane of polarized light, you might imagine that you have to resort to some really tricky chemistry in order to separate these things out. So let's determine the absolute configuration. So we've talked about R and S. And so these use the Kohn-Ingold pre-log roles. We call them the CIP roles. So what you do is you recognize your carbon stereocenter. You say this is a carbon with sp3 with 4 different groups bound to it. And there's 4, we see a bromine, a chlorine, a hydrogen, and a carbon, okay? Now what you do is you assign priorities 1 through 4, where 1 is the largest atomic number. If you're dealing with isotopes like deuterium and tritium or protium for hydrogen, then it's the atomic mass of the isotopes that get assigned their corresponding relative priorities. So let's do that. So when you do that, what do you get? Bromine's the biggest, chlorine's the second biggest, 3 is carbon, and 4 is the smallest. So we've assigned 4 different numbers. And then what you do is you draw an arrow from 1 to 3. Okay, and we notice that it's going to be counterclockwise. If it's counterclockwise, by definition, it's said to be in the S configuration, provided that the number 4 group is in the back. The back is the hatched lines, okay? If the number 4 group is not in the back, what you do is you just flip it from the S to the R. And so what you can do is look at the enantiomer over here and draw here's your priorities and draw your 1 through 4. But this time, what do we see? As I mentioned, the number 4 group is a wedge. It's not in the back. So as a consequence, it looks like an S, but it's actually going to be an R when you flip it. That's the basic CIP rules application, as we see here. Diastereomers have greater than 1 chiral center. So this molecule here has 2 chiral centers as depicted by the asterisk, sp3 carbons bound to 4 different substituents. You can assign by the CIP rules their configurations and you get SR. But it's conceivable that this molecule can have 4 different stereochemical assignments to it. You can have an RR, an RS, SR, SS. So if you're opposite in configuration at each chiral center, you're in enantiomers. That's what SS and RR are. And then if you're differ and at least one of them, you're diastereomers, that's SR and SS. Those diastereomers, which differ in configuration at only one of the chiral centers, by definition are called epimers. So all epimers are diastereomers, but not all diastereomers are epimers. And we also have meso compounds. These always have an even number of chiral centers, but they have an internal plane of symmetry. And this is a fairly simple one to find. You can just imagine the molecule folding on itself. So you may have to look a little closer at molecules with even number of chiral centers to see if they're actually meso compounds. Meso compounds have internal planes of symmetry. There's no optical activity. And the 2 to the n rule doesn't apply. It's 2 to the n minus 1 stereoisomers. And so what you see here is a couple of meso compounds. You see 2 asymmetric carbons over here with the asterisk, and you can draw this plane and fold it in half. Now, you can, if you go down number 3, what you can see is that you can fold it in half actually by going through the middle of an atom or atoms, which is pretty interesting. Molecule 2 is meso, but molecule 4 is achiral. So what you see, there's no chiral centers here. So if you look at this particular carbon here, it's bound to a hydrogen you can't see. It's got the methyl group sticking out, has these 2 other groups. But as you go out, what you do is you find that these 2 other groups are actually identical. They both converge at the same point at the same time. So here's a chart of enantiomers and diastereomers. Here's pairs of diastereomers and pairs of enantiomers. You should definitely take a look at this and commit it to a thorough understanding of the differences. Now, diastereomers have different physical properties. They're not like enantiomers, so they'll have different boiling points, etc. So another twist on this is the concept of an anomer. This applies to sugars. So here's the Fischer projection of glucose, okay, on the left. Here we have all these are chiral 1, 2, 3, 4 chiral centers here. And over here, what we have is the OH. If the OH is on the right, it's called D. If it's on the left, it's called L. But what you can see here is that this OH in red is actually nucleophilic and it can attack this sp2 carbon, this aldehyde here. This is not a chiral center. It's not sp3 hybridized. By doing so, you can go from the linear version to the actual cyclical version. And the cyclical version, this carbon number 1, this anomeric carbon, is sp3 hybridized, and now it's actually chiral. And so because this OH can attack from the top of the plane, remember sp2 is planar, or the bottom of the plane, you can get an alpha, which is the down, or a beta, which is the up. So this carbon here, this sp2 carbon that turns into an sp3 carbon, is considered the anomeric carbon. So the difference between alpha D-glucose and beta D-glucose is that they're called anomers, which are a special type of epimer, which means they're also diastereomers. Now, what you see here is that the amount of alpha and the amount of beta D at equilibrium is not 50-50, but rather the alpha is less than the beta, which is 65%. So what happens then is that over time, you get a phenomenon known as mutarotation. So because this is in an unstable linkage, it can open and close, as we'll see in a moment. You can have the molecule going from a linear form to a circular form, open, close, and each time it does that, it'll arrive at an equilibrium at some point, and the beta D is more stable due to the fact that in the chair structure, you're not going to have steric hindrance amongst the groups. So here's our relationship between isomers. We see the anomers and the epimers with respect to glucose we just discussed. They're types as diastereomers, and diastereomers are a subset of stereoisomers that also go with enantiomers, and they're all under the isomer category where you have constitutional as well as conformational isomers. So let's start taking a look at some compounds. So here's alkanes, have the general formula CnH2n+2. This is for linear alkanes. If you're circular, it'll be different. An important reaction of alkanes that they do combustion. You might think about how octane in your car engine actually works. What you do is you combust it. And so what you do is you add oxygen and heat, and you oxidize those carbons completely to CO2, and you also get water as a byproduct. And the oxidation event releases a lot of energy. So there's a thermodynamic principle here of coupling. In your car engine, what you do is you couple that to the translational motion of the car. But in biochemical systems, what you do is you can actually capture that energy in the form of chemical bonds and turn it in to ATP. So combustion reactions are pretty important. So free radical halogenation is another major reaction that alkanes do. Let's take a look. So here's diatomic chlorine, and if you shine a light on it at a specific energy, you can get homolytic cleavage such that you get two chloride free radicals. And we know that free radicals are highly unstable, and in fact, they probably don't really have an activation barrier, which means whatever they hit, they react with. Tag, you're it. So these two chloride, they can react with themselves and terminate the reaction. So the initiation reaction increases the number of free radicals. But if you do this in the presence of an alkane, a simple one like methane, what can happen is that this chloride radical can yank off not a proton, but actually can yank off a hydrogen here and generate this carbon radical. Okay, so this is propagation. And when you propagate, you have no change in the net number of free radicals, but we're changing the chemistry because now what can happen is that this carbon radical can attack the diatomic chlorine that hasn't been split yet and generate an actual alkyl halide or alkyl chloride product. That's free radical halogenation. And the termination reactions occur whenever two radicals hit each other, you get a net decrease in radicals. And at some point, you're going to run out of material to propagate, and you'll ultimately terminate the reaction. So there's stereochemical considerations in free radical halogenation. So let's take a look at this compound here. So we start out with this alkane, and there's no stereo centers. This carbon here actually has two hydrogens. So although it's sp3, it doesn't have four unique groups bound to it. And so what happens then is that the chloride radical pulls off the hydrogen, as we saw, and you generate this sp2 planar intermediate here. But when the chloride radical is going to attack this, what can happen is that it can attack from the top or the bottom, because remember, if you're planar, you can attack from the top or the bottom. And when doing so, you can make different types of bonds. So you can make a bond that projects out of the plane and one that projects in the back of the plane by virtue of the position where the attack came from. As a consequence, what you see that the product, though, is actually sp3 hybridized, but now it has four different groups bound to it. So what you've done is you created a new stereo center, and what you generated is a racemic mixture, because the probability of attacking from the top is the same as the probability of attacking from the bottom. So the amount of R would equal the amount of S. And so free radical halogenation can actually generate new stereochemistry. So you always have to take that in mind when you're considering any biological or chemical reaction. So there's the S and the R. So alkenes, we can oxidize alkanes and put a double bond there. We see this in fatty acid catabolism or beta oxidation, you know it as. And you can generate molecules with pi bonds. This is 2-pentene. Notice how the numbering system is always designed to keep the number at the lowest possible. Here's cyclopentene. Here's cis-2-butene, trans-2-butene. Here's cis-retinol and trans-retinol. You're probably familiar with those in the chemistry of vitamin A and vision. Here's cholesterol, pretty hydrophobic molecule, has a double bond, so technically speaking, it's an alkene. So one of the classical reactions with alkenes is called Markovnikov addition. And so what happens then is you have these pi electrons here, and these pi electrons can come out and grab this partial positive charge, attack on the proton here, and grab it. As a consequence, what you generate is carbocation, okay? Now, you can have two different carbocations form because you can have the carbon positively charged form on this one here or that one there. And so you have a primary carbocation versus secondary carbocation. We already know the secondary is more stable, okay? So it'll exist longer. And so as a consequence, the dominant product will be where the chloride anion attacks the carbocation at the secondary position to generate 2-chloropropane. And so the major product is the most stable alkane, and this is known as Zastev's rule. So we can generate carbocation rearrangements, which also are another twist to these reactions. So we know that electrophilic addition to alkenes involves carbocation intermediates. So if we take 3-methyl-1-butene and we react with hydrochloric acid, we get a secondary carbocation formed here. But the secondary can be converted into a tertiary by just pulling off a proton and putting it over here in a 1,2 hydride shift. And then you have the chloride attacking the actual tertiary carbon cation here. Now notice that there's no stereochemistry in the product because this carbon is bound to a methyl here and a methyl there. So although it's sp3 hybridized, it's not bound to 4 substituent groups. So there's no stereochemical considerations, but there could be. Now over here, you take 3,3-dimethyl-1-hexene and you react with the hydrochloride and you get a secondary carbocation, but now you have a methyl group over here, okay? This methyl can actually shift. So what you do is you have a tertiary carbocation that reacts with the chloride anion. And in this case, you do generate 2 new stereocenters. So you get the R and you get the S. These are the dominant products. So what do you have to do? Anytime you have a secondary carbocation, what are you looking for? A reason for it to shift. It can only shift from secondary to tertiary. You would never shift from primary to secondary. Alkenes do elimination reactions. This one here, what you see is that a base can pull off a proton. Notice how the proton, or the hydrogen, I should say, we use the word interchangeably sometimes. It's probably a little sloppy, but it's basically informal. What you have is the hydrogen up and the halogen down. They're in the anti-orientation. And what happens then is that by doing so, you pull this off, these electrons jump in here. Chloride is a great leaving group. As we'll see, the weakest base is always the best leaving group. And you determine whether or not you're a weak base by the strength of the conjugate acid. Since hydrochloric acid is a strong acid, chloride must be a weak base. Let's turn to alcohols. We all have seen alcohols before. Here's N-butanol, okay, 1, 2, 3, 4. 2-butanol, okay, cyclohexanol. We see glycerol. This might be the most important alcohol we're going to take a look at because we're going to look at how to package fats when we make triglycerides, which is taking an alcohol and an acid to make an ester. Over here, we have glucose. Glucose is an alcohol. And we can also appreciate that when we start adding OH groups on the molecules, what we do is we make them more soluble. And in fact, this is a major mechanism how the liver detoxifies drugs by having cytochrome P450 enzymes add OH groups onto compounds so you can get rid of them in the urine easier. Acidity of alcohols, notice how we have cyclohexanol is pKa 17. That's less acidic than water. And as you start adding on groups, okay, what you can see is that phenol is an aromatic alcohol. So if you lose that proton, this negative charge is stabilized through resonance. So an aromatic alcohol has a far lower pKa. It's way more acidic than an aliphatic alcohol that doesn't have the benefit of resonance stabilization of the negative charge on the oxygen after you lose the proton. As you start adding more electron withdrawing groups, what you can see is that the pKa's drop to where you get picric acid. It has a pKa of 1. This is actually an explosive compound. Alcohols can be oxidized. We have primaries going to aldehydes, to acids, secondaries to ketones, and tertiary alcohols don't really react very well at all. You can bypass the aldehyde intermediate step by treating the alcohol with potassium permanganate. If you add dichromate to it, you go straight to the aldehyde. If you add more dichromate to it, you go to the acid. So we'll take a look at a couple reactions with alcohols. The first one is called the SN1 reaction for substitution nucleophilic first order. Here's the rate law. It's K times the electrophile. Okay, this is the SN1 mechanism. So here we have an alcohol with 3 different R groups bound to it, okay? R1, R2, R3. And in a polar product solvent, what we can do is generate this positively charged oxygen, and this will leave as a water forming a carbocation. What is a polar product solvent? A polar product solvent is one that is a hydrogen bond donor, such as water or ethanol. So something like acetone, as we saw earlier, although it has a carbonyl and can hydrogen bond, it only hydrogen bonds as an acceptor, not a donor. So acetone is polar aprotic. So what you do here in a polar product solvent is you form this OH2 plus, and you break this carbon-oxygen bond here. How do you break this bond? Is it immaculate conception? No, it's actually from the dipole moment of the solvent. And that's why an SN1 reaction can only occur in a polar product solvent. So you got to look at the solvent to make sure you understand how the reaction is going to work. So when you pull this off, this is the rate limiting step. Breaking this carbon-oxygen bond isn't so simple to do. So it's the rate limiting step, and that's why this electrophile, this positively charged species, this carbocation electrophile, is determinant of the rate of the reaction. So the formation of it determines the rate. Now the nucleophiles, I just have a generic nucleophile here, it could be chloride, for example, is just waiting around in solution for the carbocation to form. And when it does that, it recognizes that it's sp2 planar, so it can attack from the top or the bottom. And when it does that, it can make a bond that's going to have a wedge, or it's going to have a hatched line. And so you get an R and an S, or a racemic mixture, okay? So the SN2 mechanism is a little different. This is K times an electrophile and a nucleophile. So here's a secondary alcohol. And you know, in secondary alcohols, they're not the best of leaving groups. And I'll show you a trick with leaving groups in alcohols in a moment. So you put this in a polar aprotic solvent. And what happens is that your nucleophile can actually come in and attack from the backside. And for this split second in time, you have 5 things bound to a carbon. But as the nucleophile actually hits this electrophilic center, you leave as water. And what you can see then is that in the beginning, the attached group, the OH, was in a wedge. Now it's in a hatched line. So you inverted the configuration. Whatever the configuration was, you invert. If it's R, it went to S. If it's S, it went to R. This is backside attack. So the SN2 reaction is a function of the concentration of the electrophile and the nucleophile. So when we compare SN1 to SN2, you see the rates are different than each other. One's a polar product, one's aprotic. The order of reactivity is different. Remember, SN1 is a carbocation-based mechanism, so tertiary would be far more reactive than primary. And I would argue that primaries may not ever really occur at all. And SN2 reactions, because you have steric hindrance or access to that electrophile, that nucleophile has to navigate and get in there to hit the electrophile, that the more steric hindrance you have, the less reactive you are. So primary is more reactive than secondary or tertiary. We saw we have sp2 carbocation intermediates, pentavalent intermediates, stereochemistry, inversion, and rearrangements are possible when you go through a carbocation, but there's no carbocation rearrangements in an SN2 because there's no carbocation intermediate. So the AAMC content outline specifically mentions protection of alcohols. So while we're on the topic of alcohols, let's take a look at what that means. So what we have here is a chemical reaction. So we have, what we want to do is we want to get this carbanion here, okay, of the cyano group to actually hit this primary carbon here and kick off the chlorine and generate our desired product. But there's a problem. This molecule has an OH group on it. And since the OH group is bound to the substrate, what happens is that you get a preferred intramolecular cyclization reaction. So it's an intramolecular SN2. And this can far better compete than you can with this negative charge cyanide group here, okay? So you make this product instead. So how do you protect it? So if you modify this alcohol and eliminate the prospect of it reacting with itself, what you can do is have your desired product. So here's what you can do. You take your compound, your alcohol, you react with T-butyl alcohol under SN1 conditions. So under SN1 conditions, what you'll do is you'll make a tertiary carbocation here that will be reacted with this alcohol, and then you make an ether product here. So this is the carbocation, this is the electrophile, and this oxygen becomes the nucleophile. You make an ether, and then what you do is you react, so you've protected it by adding on these groups here. And then what you can do is you split the ether, and the way you split or react ethers is with strong acids and probably some heat. And when you do that, what you can do is actually generate your desired product and eliminate what you don't want here, which was the former thing that protected the alcohol. So protection of alcohols as well as protection of other groups is a way of eliminating the functionality of how some groups interfere with others' chemistry. That's specifically listed on the AAMC content outline. And so is the preparation of mesylates and tosylates. So I mentioned before that alcohols are kind of poor leaving groups, but what you can do is you can get them in the form of an activated alcohol. And so here's your alcohol. And if you react with a compound called mesochloride or tosyl chloride, these are derivatives of basically they're sulfonate esters. That's what they are. So this alcohol attacks this electrophilic sulfur center. The chloride's eliminated, and what you generate is this compound here. And now if you react a nucleophile with it, what you can do is get this whole thing here as a leaving group. These are very good leaving groups because they're derived from very strong acids. And so the idea of a mesylate and a tosylate is to make alcohols active where you can do chemistry with them and get them to be better leaving groups because they're generally considered not very favorable leaving groups at all. So these are specifically mentioned on AAMC content outline. Let's switch over to carbonyl chemistry. There's a lot here on this slide. Here's the classic carbonyl compound. Oxygen is looking pretty big right now. So what you have, we've talked about with respect to this polar bond here, you see oxygen is really electronegative. It pulls electrons towards itself, generates an electrophilic carbon center. Aldehydes have the suffix al, ketones have -one. We see the donor-acceptor hydrogen bonding configuration as we saw before. These compounds, what you can see here, this is a ubiquinone is a ketone. This is involved in electron transport. It can be reduced to its corresponding alcohol when it's involved in electron transfer reactions. We know that these carbonyl compounds are reactive because see, we have this negative charge on the carbon here attacking this electrophilic center. What you do is you generate a tetrahedral intermediate. This one's called a cyanohydrin. That's specifically mentioned on the AAMC content outline as well. The cyanohydrin, though, this is in a tetrahedral intermediate here. Now, this tetrahedral intermediate, it'll pick up a proton, but in many cases, it'll collapse. And when it collapses, there's going to be a leaving group. There's no good leaving group on this particular molecule. That's why it stays as in this tetrahedral form. We're going to see a lot of leaving groups in a moment. So the first thing we're going to look at is acetals and ketones, and these are reactions with aldehydes and ketones. So what we have then is an aldehyde or a ketone. This is a ketone, so it's got two R's here, right? And so then you have a nucleophile, okay? And it attacks and makes a tetrahedral intermediate. When we look at the aldehyde with the H, this H is not acidic at all, okay? So this aldehyde reacts with an alcohol. We form what's called a hemiacetal, has the OR, OH, H linkage. And if you react it with more alcohol, you get the acetal, which is the OR, OR. Now, ketones can form hemiketals and as well as ketols. But one important thing to recognize is that the hemiacetal is pretty unstable, okay? But the acetal's not. Notice that the arrow goes back and forth here, but the arrow goes in one direction here. So acetals are pretty stable linkages, but hemiacetals are not. And probably the most important application you're going to find, especially for the MCAT, is with sugar chemistry. So we take a look over here. Here's glucose. If you take a look at this carbon, remember the anomeric carbon we talked about? If you take a look at this carbon, what you're going to see is that it's actually in a hemiacetal linkage. But when you actually take this carbon and put it into a glycosidic linkage here, what you see is an acetal linkage. This is a pretty stable linkage. So we've discussed before about the anomeric carbon here, okay? So the anomeric carbon is in a hemiacetal linkage in a monosaccharide. But in a disaccharide over here, what you can see is that this particular, what it used to be the anomeric carbon, is now in an acetal linkage. And there's a way to actually test whether or not you're in a hemiacetal or acetal linkage. It's called Benedict's reaction. So Benedict's reaction takes an aldehyde and monitors its conversion to an acid. So remember, this is an aldehyde. Now, if this is in an acetal linkage, it's unstable. So it could be in the open, close, goes back and forth. And so what happens if you take glucose plus this copper hydroxide solution, what you can do is oxidize it to gluconic acid. And so the blue copper will turn to red copper. That's a positive reaction of Benedict's test. So the Benedict's reaction detects the presence of available aldehydes for oxidation. But if this aldehyde is not in if it's in an acetal linkage, or over here, it won't be able to be oxidized at all. So the idea then is that if your sugar has an aldehyde, it can be reacted with Benedict's reagent. It's a reducing sugar. Here's a classical reaction for MCAT called the Aldol Condensation reaction. Here's this acetaldehyde. Here's the aldehyde group. This proton here, this hydrogen is not acidic, as I mentioned, but the guys next to it, the alpha hydrogens bound to the alpha carbon. By definition, the alpha carbon is the one immediately adjacent to the carbonyl. These are acidic. And so you can have a base like hydroxide pull off the proton. And when you do that, you get a carbanion here. And it turns out this carbanion is resonance stabilized because it can occupy here and these electrons can kick up here. So you can resonance stabilize the carbanion. We know that carbon doesn't like to be positive or negative, but if we can stabilize it somehow, then it can be around long enough to do a reaction. And the reaction it does is it attacks another molecule of acetaldehyde. And this particular molecule of acetaldehyde didn't have one of its alpha hydrogens pulled off yet. And what you make is a beta hydroxyaldehyde. And what you see here, we have an alcohol, okay? And if you take alcohols and you add a little bit of the heat to them, what you can do is, we saw earlier, you can generate alkenes and you get an alpha beta unsaturated compound. This is the Aldol Condensation reaction. Now, another thing that comes out of the aldol is the keto-eno tautomerization. And keto-eno tautomers are structural isomers of each other. So let's take a look. Here's acetone, okay? Acetone has alpha protons. So we pull off the actual proton with the base. We have a resonance stabilized carbanion, which you see here. This resonance stabilized carbanion is called the enol-8, okay? Enolate. If it picks up a proton, it's called an enol. The enol is a constitutional isomer, a tautomer of the parental compound. Now, what you see down here are keto-enol equilibriums here. And what you see in the case of the top one, what you see is that the arrow is drastically in favor of the keto. In most cases, the keto version is predominantly the most stable. There's 99% will exist in the keto form. But there are some exceptions, and a major exception is phenol. This is the phenol. So phenol has a keto version, but what you can see is that the arrow is heavily in favor of phenol, the enol, because of resonance stabilization. Now, you should probably be aware of tautomers in the context of nucleic acids. And so if you've read Watson and Crick's The Double Helix books, it's pretty good because during the discovery of DNA, they have this big conundrum about whether or not the base pairs exist in the keto or the enol form. So we see over here keto versus enol. And what you can see is that there's alpha hydrogens right here that you can have a base pull off. And what you can do is you can take these base pairs and make the enol versions of them. Okay, here's the enol right here. And what you can notice then is if you take a look at the parental molecule, the keto, this is a hydrogen bond acceptor. But in the enol form, it's a hydrogen bond donor. Now, remember the importance of hydrogen bonding and base pairing with CG having 3 and AT having 2. So when you start having these keto-enol tautomerizations occurring in nucleic acid chains, then what you can generate are mutations because in the enol form, thymine binds to guanine through hydrogen base pairing. And so what happens then is this, if it happens 1% of the time, but you have 3 billion base pairs, 1% is come up in the world. That's actually significant. So every time the DNA polymerase is coming through, it may see thymine in the enol form and lay down a guanine by accident. Now you have mechanisms that go back and fix it, but this keto-enol tautomerization is an intrinsic way to introduce mutations into nucleic acids. There's also another thing called kinetic and thermodynamic enolates. So this concept of kinetic versus thermodynamic is a big deal in the MCAT. You're bound to see something like this at some point. So what we have over here is a compound, okay? It's a ketone in a cyclical structure, but now there's 2 alpha protons. You don't see them there. They're there though. There's 1 here and there's 2 over here, but they're in different, they're not the same because there's a methyl group over here on the right, but there's no methyl group over here. And what you can do is if you're going to make an enolate, you can pull a proton off from the one by the methyl or a proton off on the one on the left. You get 2 different products. The question is, which one is the kinetic product? Which one is the thermodynamic product? The kinetic product is the one that's formed the fastest. The thermodynamic one is the one that is the most stable, okay? And in some cases, but not in this case, the thermodynamic and the kinetic product can be the same. So if you take a look over here, what you see is that on the left, these hydrogens are the least sterically hindered. They're the easiest accessible for the base to pull the proton off, so it's going to form faster. So product 2 is the kinetic enolate. But over here, product number 1 forms the more substituted alkene. So using Seystaff's rule, where the most substituted alkene is the most stable and favorable one, product 1 is the thermodynamic product. We shift over to other types of aldehyde chemistry. Here you see a reaction with a primary amine. A primary amine is often going to look like a lysine. In this case, it's unprotonated, okay? But so what happens then is that you have a primary amine plus an aldehyde or a ketone gives you an imine or a Schiff base. This is a very common reaction in biological chemistry. It's all over the place. It's how vitamins like pyridoxal covalently link to their enzymes. It's involved in vision. You're going to see this reaction a lot. Now, we have the mechanism in our diagnostic test. I'm not going to bother with the mechanistic details right now, but you can imagine that the lone pair of electrons attacks this electrophilic carbon here, making a tetrahedral intermediate. But as the tetrahedral intermediate gets manipulated, you're going to ultimately kick out the oxygen, and you're going to have the C double bond N forming. So a primary amine and an aldehyde or a ketone gives you a shift base, which is also known as an imine. Here's an enamine. So what you have here is an ene, a double bond, and an amine. And what you can see is that this lone pair can have a resonance structure where you get a positively charged nitrogen and a negatively charged carbanion. That negatively charged carbanion is reactive. And so it can do an SN2 on this methyl group here, and you can actually alkylate it, okay? So you have to think about resonance structures and how they generate carbanions that are resonance stabilized, and those carbanions can actually be nucleophiles and attack electrophiles in various types of reactions. Let's switch over to carboxylic acids. So this is a formic acid or methanoic acid. Here's pyruvic acid. You should definitely commit this to memory here, okay? Here's 4-methylhexanoic acid. Notice that the carbon in the carboxyl group is always the number 1, 2, 3, 4. 6-chlorohexanoic acid, 1, 2, 3, 4, 5, 6. And there's benzoic acid and levulinic acid, which is a precursor in heme synthesis. So one very straightforward thing about carboxyl groups is the biotin cofactor, vitamin B7, actually adds carboxyl groups onto substrates. So this is the rate limiting step in fatty acid synthesis. As you imagine, it's regulated by hormones. As you can see here, when you have a lot of insulin, you're going to make more fat. So we can take acetyl-CoA as a substrate, make malonyl-CoA, okay? We can also decarboxylate too. We can yank off carboxyl groups. One thing is acetoacetate or acetoacetic acid. Acetoacetate is a ketone body, and ketone bodies are made from excessive fat breakdown in the liver. But these can spontaneously decarboxylate. And when you spontaneously decarboxylate, you get a resonance stabilized structure and you can make acetone. So the synthesis of acetone, as in diabetics, for example, is non-enzymatic because it's spontaneous. Now, pyruvate over here is decarboxylated in the pyruvate dehydrogenase complex. This is in the actual mitochondria. So pyruvate is the terminal product of glycolysis, and then you throw it into the mitochondria. You get rid of a carbon in a thiamine, a vitamin B1 dependent reaction here, thiamine pyrophosphate, TPP, and you make acetyl-CoA. There's decarboxylation reactions. So there's a lot of carboxylic acid derivatives. We're going to look at 4 of them. Acyl halides you see here. This is acetyl bromide. You can synthesize them from alcohol and phosphorus tribromide. There's also acid anhydrides. As you can see here, this anhydride looks like it's generated from 2 carboxylic acids that came together. There's esters here. This is ethyl acetate or ethyl ethanoate. So an ethyl acetate, what you do is you always name the thing on the right first. So there's 1, 2 carbons. So that's the ethyl. Amide, this is N-methyl acetamide. So we're going to go through all the reactions. You should understand how you make them and how they react. We can see a number of things are going to be important biochemically, particularly esters and amides, esters with triglycerides, amides with protein chemistry. So here's acyl halides. Let's react it with water. So water is in an equilibrium. The hydroxyl will be a stronger nucleophile. It's more negatively charged. It attacks the electrophilic center. You make your tetrahedral intermediate. It collapses and the halogen leaves. Halogens are great leaving groups. They are the weak conjugate bases of strong acids. And as a consequence, you make an acid, and if the pH is right, it'll ionize. Now, you could take an acyl halide and an acid, and this negative, these electrons on this oxygen, this negative charge here will react as the nucleophile, make a tetrahedral intermediate. So acyl halides and acids make acid anhydrides. You can react with an alcohol to get an ester. So carbonyls plus alcohols most often give you esters. Acyl halide plus ammonia gives you an amide. And so the reaction mechanisms are all analogous to what you see in reaction number 1. You have a nucleophile attacking the carbonyl carbon. It's electrophilic. Tetrahedral intermediate forms, and it collapses, and you generate a new product. So acid anhydrides are synthesized from 2 carboxylic acids, as you see here. Okay. If I react an acid anhydride with an alcohol, I get an acid plus an ester. So anytime you have a carbonyl and an alcohol, you're going to get an ester. Here's the synthesis of an ester. So this is palmitic acid. This is a carboxylic acid. This is the fatty acid that's made from fatty acid synthesis. So when you convert excess carbon into fatty acids in your liver, for example, you generate palmitic acid. It's the most abundant and common of the fatty acids. But you should recognize that fatty acids are always going to be activated. And when they're activated, you use ATP and you generate their CoA derivatives. These are thioesters. Thioesters are very reactive. So they're more reacting to carboxylic acids. So you always activate acids with ATP. And what you can see here then is now you have palmitoyl-CoA. And what you can do then is take glycerol, which is a 3-carbon alcohol, and you can have one of the alcohols actually do a reaction. So what you end up with is you started with a thioester and you end up with another ester. So it's a trans-esterification reaction. And what you've done is you've actually esterified one of the alcohol groups in this particular glycerol 3-phosphate molecule. You can hydrolyze esters, of course. So here you hydrolyze. If you hydrolyze an ester, what you're going to get is an alcohol and an acid. So therefore, in order to make an ester, you can add an alcohol with an acid. Here's a cyclical ester. It's called a lactone. So lactones are pretty important biological molecules. And so here we have water hydrolyzing it. It comes in as a nucleophile, attacks that electrophilic carbon, and you open up the ring. And I showed you earlier that triglycerides are linked to glycerol acids. So the take-home message is that esters plus water give you acids plus alcohols. There's a reaction for esters. It's very analogous to the Aldol condensation. And so if you look at the ester up here in this particular one, what you see is that you have alpha protons too. So any proton next to a carbonyl carbon is going to be an alpha. And so they're acidic as well. And so in this case, what you do is you pull the proton off. You have a resonance stabilized carbanion that attacks another electrophilic carbon, and then you form these products over here. So it's very analogous to the actual Aldol condensation. What you see here at the bottom is that once you pull off that hydrogen, what you get is a resonance stabilized carbanion. So we see a very similar set of reactions. So these reactions look complicated, but you should think about them. They all follow the same logic over and over and over again. So what we see here is that how to make an amide. So we have methyl acetate, an ester plus an amine. The amine has its lone pair, it's a nucleophile, attacks the electrophile. Now, this particular reaction was done in acid, so as a consequence, you protonated the oxygen. Since oxygen is so electronegative, there's no better way to make it angry than to protonate it. So when you protonate it, it forces itself to pull more electrons towards itself, and it makes even a larger positive charge on that electrophilic carbon here. You add a little bit of heat, and what you end up with is basically an ester plus an amine gives you an amide plus an alcohol. Take a look at those reactions a little closer. So you can also get diethylamine plus acetyl chloride, giving you NN dimethyl acetamide. And we can have an amine plus an anhydride, give you an amide plus an acid. And there's also the transamination reaction where an amine plus an amide gives you an amide plus an amine. So they may look complicated, but when you sit down and you think about what's a nucleophile, what's an electrophile, tetrahedral intermediate, leaving group, these will all become very simplified for you, no matter how complicated the structures appear. Peptide bonds, of course, are amide linkages. They're planar. We all seen that with proteins. So let's hydrolyze a peptide bond. What you have here is a peptide bond hydrolyzed by water. What this lysine residue does, it pulls off a proton here, generating an OH minus, the stronger nucleophile. This is how enzymes catalyze reactions. Attacks it. Notice how this oxygen was hydrogen bonded to a serine, giving it a partial positive charge, making this electrophilic center larger and even stronger for the nucleophile. And what you do is you hit it and you form a tetrahedral intermediate that collapses. And now what happens is that you hydrogen bond with the positively charged nitrogen and hydrogen in the lysine residue here. And what you can do is make a better leaving group, because the best leaving group is the weakest base. So you have NH versus NH2, and NH2 is a much weaker base. So the reactivity. So the relative reactivity of carbonyl derivatives. So it basically goes where you have acyl halide, anhydride, ester, and amide. So amide is the least reactive, which means it's the most stable. And if you look at the reason why, you take a look at the weakest base. Chloride is the weakest base. This is the conjugate base of a strong acid hydrochloric acid. This is a carboxyl group. This is basically an oxyanion. That's not really a great, it's actually pretty, it's more stronger than the chloride for sure, but it's not as strong as NH minus. That's a bad leaving group. So notice in the last reaction, what we did was we added a proton to it to make it NH2. And NH2 is much easier to leave than NH minus. With that's all we got. So go to our website, Organic Chemistry Diagnostic